Smoothing means converting this which is the output from the bridge rectifier to this. A dead straight, dead flat DC line. So just to state again, this is the output from the bridge rectifier, full wave rectification, and that's too much ripple. It's too uneven and it will cause problems, so we need it to be nice and straight and level, as if it was a battery. So to recap the circuit that we looked at earlier, here is our transformer, and this would be possibly 230 volts AC coming in, and we would usually step down to most of our electronics, perhaps 5 volts, 12 volts, 24 volts, whatever the circuit is that we're feeding. And this is the bridge rectifier. I've drawn it in a slightly different way to that on the previous handout, simply because when it comes to exam time, these are very popular questions and there's more than one way to draw the bridge. So transformer, bridge rectifier. Over here we would have our load. And the problem is, in this circuit, the current that is delivered to the load will have a shape like this. So it's not particularly useful. And how do we deal with that? There are many different ways, but the simplest and one of the most effective is to stick, my paper moved, apologies, is to stick a huge high value electrolytic capacitor in parallel with the load. I'll show how this works in just a moment. So this is what we're going to do. On your handout, I haven't drawn this, I've done this. So we have AC in. This is your transformer. And this then goes into a bridge rectifier. And the input to the bridge, 4 terminals, AC, AC, output, positive DC, negative DC. So you can label your diagram up accordingly. This is point A and this is point B. I'll call this A and A dash, B and B dash. In the waveforms which follow, I'll consider just the output from the bridge, and then I'll consider the effect of including the electrolytic capacitor in parallel with the load. Okay, so let's have a look at that right now. Here is the output from the transformer. So this is simply AC. We then put it into the rectifier, and that will give us this. So the output from the rectifier is full wave rectification. What we need to do is to put a capacitor in the circuit, and what will happen now is this. You may be able to make out on the video that I've drawn in pencil this. So I've taken the output from the bridge rectifier and now we're going to consider it one step at a time. The output across the load with the capacitor is going to do this. So this is the first part of the cycle, it's rising. At this point in time, the supply begins to change. But on this rise, the capacitor has charged. So as soon as the voltage across it falls below the voltage on it, the capacitor will discharge and it will give up some of its energy, and it will do something like this. So as time goes on, the supply from the rectifier is going down and it's rising again, and at this point it will begin to charge the capacitor again. So we're charging the capacitor again. Here the voltage across it falls and the capacitor will discharge. Doing so, At this point it's rising again, and it will charge, discharge, charge, discharge, charge, discharge. So hopefully you can see that the effect of introducing the capacitor is to greatly reduce the ripple, the variation in the output from the rectifier. This isn't perfect, but it's much better than it was before, and with additional components, which takes us beyond the scope of this course, we can improve this to a perfect flat DC level.